All right. So this problem involves a sled going down a hill, and it's a bit of a mixture of a kinematics problem and a forces and free body diagram type problem. So part A, right, is purely a kinematic question. You don't need to do anything with forces. The important part is we're told in the text of the problem is that it's traveling at a constant speed. So once you know it's a constant speed, you can use sort of that easy relationship that you remember from, maybe way back in middle school of where that relates velocity, distance, and time, right? So for part A, all I would do is I'd say that the distance we travel, x, equals the velocity we're traveling at times the amount of time that it takes. Since we want to solve the amount of time, and we know the distance and velocity, this is pretty straightforward, right? So the distance, 21 meters, the velocity, 2.4 meters per second. And if you plug all that in, you get 8.75 seconds. Right, so that's part A. Again, I want to reemphasize, though, yes, this is a really, really, really fast and easy part. But if you don't put something like that to show what you're starting with and what you're going to use, you don't get full credit on this problem. And there's no reason to miss points on this easy part, right? The later parts will be harder, so make sure you're always setting up your work. All right, part B. Now we're going to start talking about forces a bit more. We have the sled on an incline, right? And we want to know what forces exist. Well, there's two that are obvious. The sled does not fall through the surface of the hill, so there has to be a normal force, right? Labeled normal force. And the sled has mass, so there must be a weight. Actually, that's a little bit tilted. Right? So there must be a weight, or a force of gravity, or whatever you want to call it. And so now, at this point, those two you definitely have to get. However, the fact that you're told it's traveling at constant speed tells you there must be a third force, right? If only these two forces exist, there's a net force that would point down the incline, right? That would exist if I added those two vectors. Since it's a constant speed, we can't have that net force. So I have to figure out what the other force is, which, again, from the context of the problem, should make sense. It's got to be friction, right, that opposes the direction you're moving in. And specifically, it's kinetic friction because you're in motion. And that kind of also makes sense from the wording of the problem, right? A muddy hill is going to have friction on it. It's not slippery. So three vectors, right? Three forces. All right, so part C, if you did your free body diagram correctly, part C is pretty straightforward. We know it's constant speed, so that tells us that, and we care about the frictional force. So we're going to talk about horizontal forces, because that's what the frictional force is. And we know that the net horizontal force must be 0, right, by definition. Right? So in the horizontal direction, right, we have two forces. The first is the obvious friction force, and the second is this component of the weight, right? This is going to be mg sine theta, right? The down the hill part of the weight, mg sine theta. And so now we can plug in those forces into this net force statement. Mg sine theta is down the hill, so that's our positive direction. And the force of friction is up the hill. So that's our negative direction. That net force is 0. And now, you might think to yourself, oh, do I need the normal force to use the definition of friction? No, you have to read the question carefully. It asks just for, what is the frictional force? That's the thing we're trying to solve for. So all I need to do is rearrange to solve for that. Right? This is the answer to the frictional force is question. And so we plug in the numbers, 25 kilograms, 9.8 meters per second squared, and the sine of 15 degrees, because we're told the hill is tilted at 15 degrees. And you plug all that in, and you get 63.4 newtons. Right? So that's our final answer for part C. Okay? All right, So we've got the frictional force. Now the next question, part D, is asking us for the actual coefficient of friction. So we know that by definition, friction is fun. So if we knew the normal force, we could solve this. But we don't directly yet know the normal force. However, we know something about the normal force. That's a vertical force. So if we want to figure out this, then we need to say the net vertical force is also zero. It's not accelerating up or down. And we have two vertical forces, right? The normal force points up and part of the weight points down, right? If I go back to my free body diagram, that's this piece right there. That right there is mg cosine theta, right, from geometry. So we have an equation that we can then use to solve for the normal force. And again, we can plug in the numbers, right? Although actually it's going to turn out it's easier not to plug in the numbers in this case, so I'm not going to solve for it, but we could plug in those. Right? We know what the normal force is. We know mg and theta. So now we can take this and we put it back into there. And we know the force of friction is mg sine theta, right? That's what we found from part C, equals mu times, that's a terrible mu, cosine theta, right? Substituting in. So something really nice happens. There's mg on both sides of the equation. And so if we just divide both sides by cosine theta, we get mu equals sine theta over cosine theta, which is tangent theta, which is then plugging in the angle, 15 degrees, which is 0.27, right? And one thing to note again, when I emphasize setting up work, there's a reason. If all you can do in this problem is write that statement right there, that you know a relationship between the coefficient of friction and the frictional force, that's 1 point out of 3 for this section, right? Set up your work. All right, and so now part E, we have a describe and then graph parts, right? So describing, I'm going to do without writing because I'm just going to talk about it. And then the graph I'll make. So we're told that it's at the bottom of the slope, and now it's on horizontal ground, but friction doesn't change. So what happens to the net force? Well, on the horizontal ground, right, it's going to look like that, right? There's no longer part of the weight that points sort of down the hill. There's only one horizontal force. That means the acceleration has to be negative, and it has to decrease the velocity of the sled. But since the frictional force is a constant force, right, mu times n, the normal force isn't changing on the horizontal ground either, it's a constant slowing down. So it's making some statement about that it slows down and the acceleration is constant while it slows down is what you're trying to do here. Right, it says in terms of velocity and acceleration, that means you have to address both of those. Something about the velocity, it decreases. Something about the acceleration is a constant negative number. Okay? So now the graph. They give you the axes, so you don't have to worry about setting it up. And we want a graph of the speed versus time, first on the slope, and second on the flat ground. So I'm going to label a time I'm going to call TL, the time that it leaves. So the first part should be very, very easy, right? When it's on the slope, the problem tells us it's a constant speed. What's a constant speed on a graph? It's a horizontal line. So that's the first part. Then if you did E part 1 correctly, the second part is pretty straightforward too because you already described it. It has to decrease, and since the acceleration is constant, it has to have a constant slope, right? And so it's going to look something like that, right? That's the only type of motion that fits the description. However, there's something, once again, if you just get this right here, if you can't figure out the rest of the problem, if all you can do is read the problem description that it has a constant velocity when it's on the hill, that's 1 out of 2 points. Everyone should get that point. The second one, maybe a little bit tougher. All right? So that's the motion of this sled sort of on the hill and on the ground and the forces involved.